To continue our series on complex numbers, we're going to dedicate this lesson to multiplying complex numbers. So sort of the goal, I suppose, is to figure out what happens when you are taking two complex numbers, let's call them z sub 1 times z sub 2, so a1 plus b1i, and multiplying it by a2 plus b2i. So figuring out how that works. So the first thing I want to do here is I want to remind you, and this is something that we will use extensively through this lesson, of the definition of I, right? So I is the number whose square is -1, okay? So keep that in mind as we start moving into this next discussion. So I'm actually going to dive straight into an example. So say that I have the product of the following two numbers. Say that I have 2i times 7 minus 3i. These are two complex numbers. 2i happens to be purely imaginary. That's fine. 7 minus 3i is complex. It has a real part and an imaginary part. What's really cool and sort of comforting is that even though this is a new family of numbers, we've expanded the reals to include this new number called I, a lot of the properties that carry over from the real numbers are still here for us. So for example, the distributive property. The distributive property would have us multiply the 2i by 7 and the 2i by -3i. And that's exactly how we proceed. 2i times 7 is 14i. 2i times -3i is minus 6i squared. So you might be looking at this and you might be thinking, wait a minute, but so what? So I guess this is like a new kind of number. It has an I squared in it. Well, careful. Let's look at this minus 6i squared piece. This is where we say, wait a minute. I squared is -1. So minus 6i squared is minus 6 times -1, so it's actually plus 6. So it turns out that 14i minus 6i squared is actually 14i plus 6. And if we were to write it kind of in that classic order where we write the real part first and the imaginary part second, here is my real part. I'm going to abbreviate it R dot P, and here is my imaginary part, R dot P. Oops, I dot P. Okay, so anytime you multiply two complex numbers, you can write the result in the form a plus bi. So every time you multiply two complex numbers, you will get a complex number back. Let's try another example. Okay, and again, we'll multiply two complex numbers. Let's say we multiply 5 minus 2i by 2 plus I. Okay, so we're multiplying two complex numbers, and again, we're going to take advantage of the fact that the distributive property applies in the complex numbers just the same way that it did in the reals. Those of you who are interested in this kind of thing, it's really interesting that the distributive property continues to hold even though we've expanded the class of numbers we're looking at. So that's a really interesting question to kind of extend more broadly. Do all of the properties of the reals extend onto the complex? And if so, why is that? That's not a question that we ask too much in this class, but it's an interesting question to noodle on. The distributive property tells us that we're going to multiply everything by everybody, right? So some of you draw boxes to help you keep track of things. Some of you put arrows. Whatever works for you is fine for me. So let's check this out. So we have 5 times 2 is 10. 5 times I is 5i. Negative 2i times 2 is minus 4i. And then negative 2i times I is negative 2i squared. So you can already see that I'm going to have sort of the same conversation with the minus 2i squared that I had with the minus 6i squared. But before we do that, notice that we also have a pair of like terms here in the form of the 5i and the negative 4i. So what we have here is 10 plus, so 5i minus 4i is just 1i, so we'll write I, and then I'll write minus 2i squared. I'm not going to do the work that I did here again. I will let you kind of noodle on that if you'd like. So I encourage you, after I say what I'm about to say, pause the video, make sure you see where it's coming from based on this same sort of work. But negative 2i squared is actually going to be plus 2. So I end up with 10 plus I plus 2. So I get 12 plus I. Okay, so I started out with a complex number whose real part was 5, imaginary part was negative 2. I multiplied it by a complex number whose real part was 2 and imaginary part was 1. And I landed with a complex number whose real part is 12 and imaginary part is 1. So those of you who are, again, curious about this sort of thing, you might ask yourself, what's the pattern behind multiplication of complex numbers? And what you'll see, and maybe this could be something that you sort of catalog for later because you'll see a lot more of it in your later days as math students, you'll see that this actually works exactly the same way as vector multiplication. So when in your physics classes or in your calculus classes you start to come across vectors, you'll see the same sorts of patterns when you're multiplying vectors as when you're multiplying complex numbers. So secretly, without telling anybody, complex numbers are starting to hint at conversations that we'll be having later on down the line. But more about that another time. So we will do more examples, maybe one more to finish. But before we do more examples of like multiplying two complex numbers by each other, I want to take a second here and I want to talk to you about powers of I. The reason I want to talk to you about this is I'm sure some of you are thinking this. Okay, so when you multiply two complex numbers, you end up with an I squared, and that happens to work out because I squared is -1. But what if you multiply three complex numbers together? You'll get an I cubed in there. Or you could potentially get an I cubed in there. What's that all about? If you multiply four complex numbers together, you'll end up with an I to the fourth, and so on. So we should think a little bit about what happens when you multiply many, many copies of I together. So I'm going to start this with just I. I to the first power is just I. Okay? That is kind of a definition that we've accepted to be true. Anything raised to the first power is itself. I squared is -1, and that's by definition. That is how we define the imaginary number I. So now let's think about I cubed. Well, as it turns out, we know what I cubed is in terms of I squared and I. I cubed is just I to the second power times I to the first power, which is -1 times I and that's just negative I. I to the fourth power. Well, what's that? There's more than one way of looking at I to the fourth. You could think of it as I squared squared. You can think of it as I cubed times I. Whichever one is more comfortable for you. I'm going to introduce it as I cubed times I to the first, because that's in line with how I taught you the I cubed. And we know, because we just did it, that I cubed is negative I. So that means I to the fourth is the same thing as negative I squared. I squared, though, is negative 1. So that means that I to the fourth is just 1. So let's make a little table here of the first 4 powers of I. So I to the first is I squared is negative 1. I cubed is negative I. And I to the fourth is 1. Why did I make kind of a big deal of this, put it in a box and so on? Well, because what's I to the fifth? Well, in keeping with the way that we introduced I to the fourth and I cubed, I to the fifth is just I to the fourth times I. And since I to the fourth is 1, well, I to the fifth brings us back to I. I to the sixth, well, that's just I to the fifth times I, which is I times I, which is I squared. So what I hope you all see here is we have 4 distinct powers of I, and then we come back to the beginning. So I is only capable of having 4 different outcomes for its powers. I, negative 1, negative I, and 1. So how does this play out in terms of a weird power of I? So what's I to the power, I don't know, 23? I made 23 up off the top of my head. Well, remember, every 4th power of I, you're going to end up with 1. So I to the 4th is 1. I to the 8th is 1. I to the 12th is 1. And so on. So what that's telling me is figuring out what I to the 23rd power is kind of like seeing how many times 4 goes into 23. And then more importantly, what's left over. Well, answer me this. How many times does 4 go into 23? So, in other words, kind of what's the smallest, what's the largest number divisible by 4 that's less than 23? And the answer is 20. So that's 5 4s. And then what's left over? 3. So since I cubed is negative I, and I to the 4th is 1, what I have here is 1 times negative I. So I to the 23rd power is the same as I cubed. Let's try that one more time. Say that I had I to the 42nd power. Okay? So same thing. In a sense, you're dividing 42 by 4. You're kind of disregarding those complete cycles of 4 inside of 42. You're just looking at what's left over. So you tell me, how many times does 4 go into 42? Right, 10. Which is 40. And then you have 2 left over. So I to the 42nd power is the same as I squared, which we know to be negative 1. So anytime somebody asks you for a power of I, all you're really looking at it is how many clean cycles of 4 are there, but more importantly, what's left over after I take out all of those clean cycles of 4. And then that is the same as your power of I, okay? So what's kind of cool here, and this is actually a small example of something that we in mathematics call modular arithmetic, is that any power of I, whether it's I to the 4071st power, or I cubed, or I to the 29th, every single one of them is going to be one of these 4 values. It's either going to be I, -1, negative I, or 1. So this concludes our lesson on multiplying complex numbers. We did a couple of examples of working with multiplications, and then we talked about powers of I. In our next video, we'll talk about dividing complex numbers, and as part of that conversation, complex conjugates.